Hi all, and welcome back to the Crazy Small CPU video series. We're getting up to the end of the data wiring, and the last time I spoke to you we'd wired up the data bus from the ALU over to the RAM. I've just added a few more lines from the ALU up to the flags register, and in today's video I'm going to talk about both the RAM chip and the flags register. I've also got it ready to roll, so we can do some demonstrations, but just before we get to that, I'll go through how the ALU and the RAM interface with each other. I still haven't got my printer to work, so here's an electronic version of the CPU, the logical diagram, and this is actually version 2. So you can see we've got both A register and B registers connected to the multiplexer. They feed data into the ALU, and now what we're talking about is the connection between the ALU and the RAM. So out of the 8 bits that comes out of the ALU, 4 bits are going to be written down the data bus and over to the RAM. The flags bits, another 4 bits, will come out of the ALU and get stored into the flags register. Okay, but now the data bus is not just single directional, because we also want to be able to get stuff out of the RAM and into the multiplexer so that we can load stuff that we've previously stored in memory. So let's have a look at the RAM chip. And you'll notice that it pretty much has exactly the same pin layout as the ROM chips. So here's a ROM chip, the ALU, and we've got exactly the same layout of pins for the RAM. The interesting thing is that the ROM chip has got write enable, which of course we use for when we're programming it. It's an EEPROM, but we're actually going to use this one all the time for using the RAM. Okay, so the ALU spits out 4 bits, which are going to go down and be stored as the flags in the flags register. But more importantly, bits 4, 5, 6 and 7 of the output are going to come out of the ROM and go down the data bus and be stored into RAM. But we have a bit of a problem, because we also want to be able to write out from the RAM and put it on the same data bus so that we can send it down to the multiplexer. So we need to tell both devices whether to assert their output or whether to go into high impedance and not put anything out onto the data bus. So we've got our first control line, which is RAM write, and RAM write's connecting all 3 of these chips together. When RAM write goes low, the output enable pin on the ALU is enabled, and that means that the ALU will output its results onto the data bus and they'll go down to the RAM chip. At the same time, this wire is connected up to the write enable pin on the RAM chip, and that allows the RAM to receive writes. So in other words, we can write to the RAM chip when that pin goes low. So it's lucky coincidence that both of those are active low. That when the ALU is doing its output, the RAM chip is also being able to be written. And also coincidentally, we've got the load line on the flags, which is also active low, so that when this goes low, the ALU puts its output, goes out to the RAM, and these 4 bits also go out and can be written into the flags register. Now when RAM write is high, we're not enabling output on the ALU, on the ROM, and so the ALU will be putting out high impedance. It won't be putting anything out onto the data bus. The write enable pin is now high, so we're not trying to write to the RAM, which basically means that the RAM chip is set up to be outputting its values onto the data bus. So we're really lucky that we've got 3 chips, all with active low lines, that all can interface with the same control line without any extra logic chips. So if we come back to the schematic with the ROM chip for the ALU over here, we've got the 4, 5, 6, 7 lines now being wired up over to the RAM chip. That's effectively the data bus. And I've just added in the lines 0, 1, 2 and 3, which are going to go up and be inputs to the flags register. I also noticed that I'd made a mistake on my drawing, so the RAM write line should go both to the output enable on the ALU, up to the PE line on the flags, and also if we follow it over up to here, RAM write, and all the way up to the write enable pin on the RAM chip. I've not wired up the address side yet, so when we get to testing, we're actually going to have to physically manually put in our own addresses to get it to do the right thing. And that's what we should do right now. But before we bring the breadboard back and wire it up and start it and test it, let's just see what I'm going to try and do with it. So here's a simple program I'm going to try and manually run to test out that the RAM chip is working. I'm going to load into the A register the number 2. So that means I've got to set A load active, and it's active low. Once we've got 2 in the A register, I'm going to pass it through the ALU, and I'm going to write it out to RAM. And I'm going to write it out at location 0. Once we've got 2 safely in location 0, I'm going to do the same thing again, but this time I'm going to load the number 9 into the A register, and I'm going to write it out to memory at location 5. Okay, so now we should have number 2 in location 0, number 9 in location 5, and we should be able to test that we can read back from RAM. So we're going to load from memory from location 0, and that means I now have to set the multiplexer select line high, so we're reading from memory rather than reading from the address bus. And of course I need to set the A load line active low to load into the A register. I should at this point see the A register set up with the number 2. Then I'm going to do the same thing with RAM location 5, and at this point I should actually see the number 9 appear in the A register. So I've actually run this in simulation with my CPU simulator, and you can see what happens. That on the first instruction A gets set to 2, on the next instruction RAM position 0 gets that value, then we do A loaded with the number 9, RAM location 5 it gets set with the number 9, and then finally when we do the load from memory instructions, we get back the number 2, and then we get back the number 9. Okay, back to the breadboard, and this time I've got a whole bunch of wires already wired in and labelled up, so let's have a look at what we've got. I've got the ALU doing pass A already hardwired. I've got my control line RAM write, remember active low, to write stuff into the RAM. Got an active low line to load the A register. I've got my select line for the multiplexer, and I've got 8 bits of address, so I can put that and choose the address for the RAM. I've got 4 LEDs showing the output of the A register. Remember they're backwards, so most significant bit is to the right. I've got 4 LED bits for the ALU, the output of the ALU. Actually, that's the output of the data bus, so it depends on whether we've got RAM write high or low as to what that's showing. I've got 4 LEDs for the flags, and I would love to have 8 LEDs for the RAM address, but there's only room to wire in 4, so you're going to have to trust me when I'm putting the addresses in. Okay, so the first task is to actually load a constant 2 into the A register. So I've got A cell low to read from the address bus, I've got A load, so we're actually going to load, and I've got the number 2 on the address bus. So hopefully if I press the toggle, we now have the number 2 into the A register. Now with RAM write still high, what we're seeing on the 4 LEDs down here is what is the value in location 2 in memory, which is just looks like F at the moment. Okay, so now let's go back to memory location 0, and you'll notice that the value of the data bus has changed because now we've got different memory address, so we've got different values. Alright, let's write this out to RAM. I'll just stop the address A register from being loaded, and now if I just quickly pick up the RAM write line and drop it down, the number 2 is being asserted on the data bus, and that should be loaded into RAM at location 0. If I move the RAM write light back to high, now we've actually seen what's in the RAM chip, and we have the number 2, so it looks like it's been stored safely. Okay, so now let's load the number 9 into the A register. So let's go for 1 and 8, which makes the number 9. So on the data bus, we've got what's in location number 9, but I'm more interested in loading through the multiplexer into the A register the constant 9. So now we have the constant 9 into the A register, and I'm going to load that at position 5 in memory. So let's set up address 5. Okay, address 5 has got rubbish in it at the moment, but hopefully if I now drop RAM write low, we're asserting number 5 on the data bus. It's going into RAM, and if I bring that back high, we now have the number 5 at location 9. Oh, sorry, the number 9 at location 5. All right, now let's see whether we can read from the data bus down into the multiplexer and into the A register. Okay, so let's go back to location 0. Remember, location 0 should have the number 2 in it. And yep, we've got RAM write high, so therefore the data bus is showing the contents of the RAM, and there is the number 2 in there. So if I now load the A register, excellent, we've got the number 2 back there. And if we go to position 5 in memory, so that's 1 plus 4 is 5. The data bus is showing that we've got the number 9 in there, and if I hit the clock button, we've loaded the number 9 into the A register. Excellent, so it looks like the data path through the CPU is working fine. I haven't touched on the flags yet, so I need to talk about that. Okay, time to look at the flags register. Now, the flags register is a 74LS161, the same as what we're using for the A register and B register. Let's just check it out. So what we should be able to do is load a constant into the A register, pass it through the ALU, and as we update the ALU, we should actually see something on the flags. So let's start with the number 1. The 1 is not 0, not negative, so at the moment the flags register is showing no lights. But let's change to the number 0. I've got constant 0 here. I'm going to load it into the A register. Alright, so now we have constant 0 here. Remember, the ALU is combinatorial. It produces its output straight away. We've got pass A happening. So the output of the ALU is also the number 0. So the question is, why hasn't the flags register been updated to reflect that we now have a 0 number on the output? It's sequential. So we've loaded the A register with 0, but that happened on 1 clock pulse. We still haven't loaded the flags register with the output from the ALU. So now we need to assert RAM write low and do a 2nd clock pulse. And now we've got a light lit up to say that the number is indeed 0. So let's put the number 8 into the A register. So I'm going to raise the 8-bit high. I will press the button to load the A register. Alright, so we load the A register, and immediately, because the ALU is combinatorial, the output is out there. But we loaded the value and it didn't get a time to get through the ALU to be loaded into the flags register. So the flags register is still storing the result of the previous ALU operation. So now when we press the clock pulse the 2nd time, we now have the top LED lit, which says that indeed the number is negative. It's got the high bit set. So you've got to remember, when you're doing things on a CPU, that every sequential circuit is an extra clock pulse to get from place to place. So it does look like the flags register is working, looks like the RAM's working, we know the multiplexer is working, we know the 2 registers are working, we've checked out the ALU, so our whole data path is working. Excellent. So in our next video, we should be able to move on to the control side. So what I plan to do on the next video is to just get the program counter counting, and then probably in the video after that, we'll wire the addresses up to the 2 ROMs and probably actually try to run our first program. Anyway, that's enough for now, and I'll see you on the next video.